January 1943. Somewhere in the Atlantic, a convoy creeps eastward, its ships swallowed by fog thick enough to mute even the sea's own breathing. For a moment the ocean feels unnaturally still. Then, a single hollow boom rolls across the water. Men rush to the rails. A plume of spray rises behind a distant merchantman, illuminated only by the faint glow of its running lights. It was this very moment that was the turning point for the British in World War II. Britain had a weakness that, if it wasn't addressed soon, the war would be lost, thus spawning an invention so absurd, so powerful, that history almost forgot it. That invention, Project Habakkuk. To understand why such a notion was entertained at all, we must first appreciate the scale of the problem facing the Allies. By early 1943, the Battle of the Atlantic had become a test not only of naval strength, but of endurance. Convoys were moving lifelines, grain, fuel, ammunition, raw materials, without which Britain's war effort would falter within weeks. Yet every crossing carried the same grim arithmetic. The moment they entered the Central Ocean, they stepped into a void where no aircraft could reach them. This air gap, stretching hundreds of miles, handed the initiative entirely to the U-boat packs. German submarines exploited it ruthlessly. Operating on the surface at night, they stalked convoys with near impunity, diving only when escorts closed in. Without aircraft to force them down, they maneuvered freely, coordinated attacks, and regrouped for second and third strikes. Even a single torpedo, detonating as unpredictably as the one heard in the cold open, was enough to trigger hours of panic, evasive turns, and blind retaliation. Escort ships were brave but limited tools. Their sonar could be fooled. Their depth charges required guesswork. Their firepower was designed for surface threats, not predators hidden beneath black water. And critically, escorts could not prevent what convoy commanders feared most: systematic attacks from multiple U-boats converging in darkness. The pressure on Allied planners mounted. Losses were uncomfortably high. Shipyards struggled to replace tonnage quickly enough. And though escort carriers provided some relief, they were few in number, slow to build, and vulnerable themselves. One hit to an escort carrier was not merely a tragedy, it left an entire stretch of ocean exposed for months afterwards. By late 1942, it was clear that the traditional tools of naval warfare could not close the gap alone. The RAF needed somewhere to base long-range reconnaissance aircraft deep in the Atlantic. But the ocean offered no land, no islands, not even a rock large enough to support a watchtower, let alone an airfield. So the question sharpened into something bordering on desperation. How do you create a runway in a place nature never intended one to exist? Steel was scarce, concrete impossible, and construction time painfully short. The answer, if it existed, would have to bypass every conventional material constraint Britain faced. This was the moment when imagination began to reach into extreme territory, when engineers and strategic thinkers dared to consider structures that defied the traditional boundaries of naval architecture. And it was from this crucible of necessity that a most improbable idea took form. To understand where it came from, we must explore the story behind its development. The idea that would become Project Habakkuk did not begin in a shipyard, nor in the mind of a naval architect. It emerged instead from a loose network of scientific advisors and wartime thinkers tasked with solving problems that ordinary committees could not. Within the corridors of Britain's research and planning bodies, especially those involved with combined operations, the mid-Atlantic crisis was a constant drumbeat. Convoys were still dying in the Black Pit, and the existing toolkit simply wasn't enough. It was during this period that attention turned to the one resource that seemed limitless: ice. Engineers and scientists had long noted its remarkable natural properties, its buoyancy, its enormous compressive strength, its ability to absorb enormous amounts of heat before melting. In theory, a sufficiently large structure made of ice could float indefinitely in cold waters and could be produced without consuming precious steel. It sounded fantastical, yet the war had already seen stranger ideas brought to readiness. But raw ice alone would never suffice. It cracked unpredictably, deformed under stress, and melted too easily. What Britain needed, if the idea were ever to advance beyond a thought experiment, was a new material, something that possessed the low-cost abundance of ice, but behaved more like a structural composite. Experiments in Canada provided a possible answer. With its cold climate, freshwater lakes, and available manpower, Canada became the natural proving ground for this strange concept. Early trials mixed ice with wood pulp, sawdust, and various organic fibers. Researchers found that even a small amount of fiber transformed the behavior of frozen water. Blocks that once fractured now resisted impacts. Surfaces that chipped easily now held form. And because the pulp slowed heat transfer, the mixture melted far more slowly than ice alone. This reinforced frozen composite, later known as pykrete, became the centerpiece of the idea. Demonstrations reportedly showed that a bullet fired at close range would embed itself rather than shattering the block. The material could be sawn, drilled, and shaped using ordinary woodworking tools, and it required only water, pulp, and refrigeration to produce. In wartime terms, it promised something priceless: structural strength without consuming strategic metals. As confidence grew, conceptual drawings began to take shape. The proposed vessel would be colossal, far larger than any carrier afloat. Its internal labyrinth of refrigerated corridors would maintain the temperature necessary to prevent structural creep. Refrigeration plants would run constantly, circulating cold air or brine through the hull. Above this frozen mass, designers envisioned a flight deck spanning hundreds of meters, capable of launching long-range patrol aircraft into regions no air force could previously reach. But this ambition carried weighty engineering obstacles. Scale, for one. A ship built from ice, or more accurately, a composite of ice and fiber, would behave unlike any known material. It would carry enormous internal stresses. It would expand and contract with temperature shifts. It would deform subtly under its own weight. Every element, rudders, supports, hangars, power plants, would have to be designed from first principles. Internal debates within research groups reflected these concerns. Could refrigeration keep pace with spring temperatures? Could the hull be reinforced sufficiently to carry the mass of aircraft, fuel, and defensive gear? Was it even possible to steer a vessel that, once complete, might outweigh an entire fleet? Still, the project advanced. Britain had reached a stage of war where unconventional thinking was not merely welcomed, but required. The desperate need for mid-ocean air cover meant that even daring ideas deserved a hearing. And so, as 1943 unfolded, the ice ship concept transitioned from a sketch in a meeting room to a genuine wartime proposal, one that senior figures evaluated with seriousness despite its eccentric roots. A small prototype built in Canada proved that the principle worked. A refrigerated block of reinforced ice could survive in open water far longer than expected. It was enough to keep the conversation alive. Yet for all the theory and experimentation, the world still had not seen the actual vision laid bare. What, in concrete terms, was Britain proposing to build? When all the sketches, calculations, and experiments were finally distilled into a coherent proposal, the result was unlike anything the Admiralty had ever been asked to consider. A floating airbase the size of a battleship's shadow stretched across an entire horizon, constructed not from steel or concrete but from frozen composite. The concept was bold in its simplicity. Instead of building more escort carriers, Britain would build a platform, a vast, slow-moving runway capable of hosting long-range patrol aircraft in the very heart of the Atlantic. It would not rely on speed. It would not attempt to outrun danger. Its strength would lie in sheer bulk, in the inertia and resilience of a reinforced ice mass so large that a torpedo strike would dissipate harmlessly within its outer layers. Drawings showed a structure over 1,000 feet long, with hull walls many meters thick, insulated and kept frozen by powerful refrigeration plants. Above this frozen core, a full-length flight deck would sit like a timber lid on a winter sea. Fuel tanks, workshops, stores, and living quarters would be carved into the interior like chambers in a glacier. In essence, the proposal was nothing less than an artificial island, an engineered iceberg, brought into existence solely to close the deadly gap in the Atlantic. But the real fascination lay not in the ambition, but in the mechanisms that would make such a thing possible. To understand how this improbable vessel was expected to function, we must explore the strange engineering world of reinforced ice. At the heart of Project Habakkuk lay a material so unorthodox that it challenged every assumption of naval engineering. This material, later known as pykrete, was a frozen composite of water and wood pulp. When first tested, It demonstrated properties that astonished observers: toughness far beyond ordinary ice, a reduced tendency to crack, and a surprising resistance to melting. For wartime Britain, struggling with shortages of steel and aluminium, the idea of building a vast maritime structure from such an abundant mixture was undeniably appealing. Pykrete behaved differently from traditional shipbuilding materials. Whereas steel transmitted impact sharply, pykrete absorbed it, distributing loads slowly through its fibrous matrix. Early demonstrations showed that a bullet fired at close range would embed itself rather than shattering the surface. This characteristic hinted at a form of passive resilience that conventional hulls lacked, a useful trait when the threat of torpedo or gunfire loomed large. But scale introduced new challenges. In theory, a pykrete hull several meters thick would be immensely strong, capable of shrugging off impacts that would rupture steel plating. In practice, such a hull would also be subject to gradual deformation. Like a glacier, pykrete could creep under sustained pressure, slowly altering shape unless kept sufficiently cold. Refrigeration, therefore, became the lifeblood of the design. Engineers proposed an internal network of ducts carrying chilled air or brine through the structure, ensuring that the temperature never rose above a safe threshold. Without constant cooling, the ship would quite literally sag under its own weight. Internally, the vessel was imagined as a honeycomb of compartments. This arrangement served three purposes. It provided structural rigidity, limited flooding if damage occurred, and created channels for refrigeration without weakening the hull. These compartments would be cut into the frozen mass using conventional wood-cutting tools, saws, drills, chisels, all of which were reported to work surprisingly well on pykrete's dense, waxy texture. Above the composite hull, designers planned to mount a conventional superstructure. Timber was often proposed for the decks, both because wood was readily available and because it reduced the thermal load on the frozen mass beneath. The flight deck, spanning hundreds of meters, would require steel supports in critical areas, though wartime documents emphasized that the overall steel requirement would still be a fraction of a normal carrier's. Propulsion presented a formidable question. A vessel of such staggering mass, potentially millions of tons, would not move like a warship. It would maneuver slowly, deliberately, and only with considerable power. Engineers discussed fitting large diesel-electric installations driving multiple screws. Some versions considered placing the machinery in insulated pockets carved into the hull, with exhaust conduits venting through the superstructure. Others explored using external propulsion pods attached to reinforced recesses in the hull. The exact configuration remains uncertain, as the project never advanced far enough to standardize a final layout. The flight operations concept required careful attention. Pykrete, though strong, would not tolerate the concentrated loads of landing gear without reinforcement. The deck would therefore rest on an internal framework distributing forces deep into the hull. Hangar spaces would be insulated, both to protect the aircraft and to prevent heat from eroding the frozen interior. Fuel tanks, magazines, and workshops would all need specialized thermal protection. Even crew accommodation required design compromises. Living inside a refrigerated mountain of ice demanded constant heating and carefully routed ventilation. Defensive armament, too, raised questions. Mounting heavy guns on a frozen hull required embedding supports into the composite or fixing them to the superstructure. The recoil forces of even moderate-caliber weapons had to be dispersed across large areas. While detailed plans varied, most proposals placed defensive systems atop insulated mounts, ensuring that heat from machinery or fumes did not degrade the surrounding material. Despite these challenges, tests in Canada proved the core principle. A modest prototype, refrigerated and anchored on a lake, resisted melting for months. Engineers could cut it, drill it, repair it, and maintain temperature stability with relative ease. Yet engineering theory and isolated experiments were only part of the story. The question remained: how would this extraordinary concept fit into the kind of moment we witnessed in the cold open? To understand that, we must return to the night when a convoy faced the unseen threat below. Imagine once more that convoy in the mid-Atlantic. The cold, the fog, the sudden concussion of a torpedo blooming somewhere in the dark. Escorts race to respond, but their weapons search blindly. Depth charges thunder, sonar pings echo across empty water, Yet the ocean gives nothing back. Above them, the sky remains a vast, unreachable void. In moments like these, commanders knew they were fighting half-blind. Now consider how differently that night might have felt if, somewhere beyond the horizon, a steady beam of light swept across the sea. The landing lamps of a distant runway, carried not on land, but on an artificial mountain of reinforced ice. A platform large enough to host patrol aircraft, close enough to slash the U-boat's freedom, and resilient enough to survive whatever the ocean hurled at it. This was the promise that thrilled planners, not speed, not elegance, but presence, a permanent eye watching the one place the enemy felt safest. Yet bold visions are only as strong as their performance. Before Habakkuk could shift the balance of the Atlantic, it had to prove itself not on paper, but in tests, prototypes, and engineering trials. Despite the enthusiasm of its earliest champions, Project Habakkuk ultimately confronted realities that no amount of ingenuity could fully overcome. As the engineering teams refined their designs, the scale of the undertaking grew increasingly daunting. A Pykrete carrier large enough to host long-range aircraft would require staggering quantities of wood pulp and refrigeration machinery, as well as construction facilities capable of shaping and maintaining a structure several times larger than any vessel built before or since. Cost was only one barrier. Time was another. By mid-1943, the Battle of the Atlantic was shifting. Improved convoy tactics, more escort carriers, long-range liberators, centimetric radar, and refined anti-submarine doctrine were steadily reducing U-boat effectiveness. The black pit that had once seemed impossible to close was slowly shrinking under conventional measures already in production. The urgency that had propelled Habakkuk forward began to ease. Technical assessments further tempered expectations. Maintaining internal temperatures across a hull hundreds of meters long would demand immense continuous power. Repairing damage, even superficial wear, required specialized equipment and crews trained in handling frozen composite. And because Pykrete deformed over time, the ship's shape would need constant monitoring and adjustment. What looked manageable in small prototypes became formidable when projected to full scale. Strategic planners were forced to reconsider. As one historian later observed, the question changed from, "Can we build it?" to "Should we?" The Admiralty concluded that the project, though imaginative, was no longer aligned with the evolving realities of the war at sea. Escort carriers and long-range patrol aircraft were achieving results with increasing reliability and far less speculative investment. As a result, Project Habakkuk quietly lost momentum. It was never cancelled with fanfare. Rather, it faded from priority lists, overtaken by technologies already proving their worth. By late 1943 into early 1944, the concept was effectively shelved. What remained was not a failed weapon, but a remarkable demonstration of wartime creativity, an audacious idea that belonged to a fleeting moment when the sea seemed unconquerable and imagination had to fill the gaps left by industry. But even after the project ended, its story did not simply disappear. Back on that winter convoy in 1943, the sea eventually swallowed the echoes of the torpedo blast. The fog closed in again. Escorts resumed their lonely arcs through the dark, and the merchantmen pressed onward toward Britain, exposed, anxious, and aware that the unseen enemy might still be waiting beneath them. In truth, nothing on that night could summon an airfield out of the ocean. The sky remained empty, and the convoy survived, or didn't, through a mixture of grit, discipline, and luck. But what Project Habakkuk represents is the refusal to accept that such moments were inevitable. It embodies the determination to challenge the ocean itself, to imagine a structure so improbable that it might bend the rules of warfare in Britain's favour. Although the ice ship was never built, its story lingers because it captures something essential about wartime ingenuity, the willingness to reach beyond the possible when circumstances demand it. It reminds us that the fight for the Atlantic was not only waged with corvettes and codebreakers, but also with bold ideas born in cramped offices and frozen workshops far from the front. And so, when we picture that silent convoy crossing the Black Pit, we can also picture the idea that arose from its peril, an artificial island of ice, envisioned to stand where no land existed, conceived in the hope of turning vulnerability into strength. A symbol in its own strange way of the imagination Britain summoned when the sea threatened to cut its lifeline.